Determine the natural frequency of given system.
Let us understand the given diagram. A cylindrical disc of radius r and mass m is given in the diagram, and it is pivoted at the point on the circumference. We have to find out the natural frequency for this given system. Now we know that the weight will always act in vertically downward direction passing through the center. Now to find out the natural frequency, we will make here one construction. We will consider this disc will rotate around the pivoted point on the circumference through an angle theta, and we will draw here this diagram. So here is the original disc with center G. Now when it is rotated through an angle theta about this pivoted point, I will consider this point as a O. Then this point G is shifted here and it is G dash. Now at this point G dash, there is the weight that will act in vertically downward direction, and this weight is known as mg. Now we have to draw the two components for this weight, that is one vertical component and horizontal component. So if we join this center point G dash and this pivoted point O, then here this original vertical line, that is O to G, and here O to G dash, angle between them is theta. Now this same line we have to extend, and the angle between this vertical component mg and this inclined line is also same, that is theta. So if I draw here one component passing through the center, then how we can write this component as a, because it is nearby to angle theta, so I will write here mg cos of theta. Now through the center point we have to draw another component perpendicular to this. So here this is the another component of perpendicular line, and its value is mg sin of theta. Now here this disc is rotated through an angle theta. So displacement is, the angular displacement is taking place in anticlockwise direction. So in the same direction accelerating torque is developed. So I will show the direction of accelerating torque, and how we can write here accelerating torque is I theta double dot, where I is the mass moment of inertia of this disc and theta double dot is the angular acceleration. Now if we apply the Newton's second law of motion for this system, then we can say that this accelerating torque, or it is also known as accelerating couple, is equal to summation of the external couple. Now how to find out the external couple? So for that we have to find out the forces that will act on this system. So there is only one force, that is weight, and which is acting in vertically downward direction. But here we have to find out the couple. So here this accelerating couple is in anticlockwise direction, and to oppose this there is the weight component mg sin theta, and it is acting in the opposite direction of this accelerating couple. So we have to consider this component mg sin theta. So this is the force component. So how to find out the couple? So this disc is rotated about this point O, or we can say disc is oscillating about this point O. So we have to find out the couple, that is this force multiplied by the perpendicular distance from this point O, and this distance, that is the distance between O to G dash, is R. So we can say that external couple is mg sin theta into R. So if I rotate the compass about point O in the direction of mg sin theta, then direction is in the clockwise direction. Now we will consider the signs. So suppose if I give the negative sign for anti-clockwise direction, then I have to give here the positive sign for the clockwise direction. So how we can write the equation. So we can write here minus I theta double dot is equal to mg sin theta into r. Now we will simplify this. So I will take this I theta double dot to the right hand side, then I theta double dot plus mg sin theta r is equal to 0. Now this theta is very small, so sin theta is equal to theta. So I theta double dot plus mg theta r is equal to 0. Again we will simplify. I will divide on both sides with I. So theta double dot plus mg r by I into theta is equal to 0. Now we have to find out this mass moment of inertia. Now this disk is having radius r. So we know that the mass moment of inertia of the disk is mr square by 2. But at the same time this disk is oscillating about this point O, and the weight will act through this center, that is through this point G. So we have to again consider the mass moment of inertia when the disk is rotating about this point O. So how to find out this? So for that we have to take m into this perpendicular distance from this point O to G. So this distance is r. So we can say that mi for the rotation is equal to mass into r square, that is this perpendicular distance square. So we have to add these two, mr square by 2 plus mr square. So I is equal to, so I is considered for this whole system, that is the I for the disk as well as I when the disk is rotated through an angle theta. So when we add this we will get 3 mr square by 2. Now we will put the value of I in this equation. So here is we put the value. Now we will simplify. This m is getting cancelled, this r is also getting cancelled. So we can write here theta double dot plus 2 by 3 g by r, theta is equal to 0. Now we know that the equation for the free longitudinal vibration, that is x double dot plus omega n square x is equal to 0, where x double dot is the linear acceleration, theta double dot is the angular acceleration, x is linear displacement, theta is angular displacement. So these two equations are equivalent to each other. So we can say that omega n square is equal to 2g by 3r. Therefore omega n is equal to under root of 2g by 3r. Now we have to find out the natural frequency. So natural frequency Fn, we have formula in terms of omega n, that is omega n by 2 pi. So Fn is equal to 1 by 2 pi under root of 2g by 3r. So this is the equation for natural frequency for the given system.